Solubility and Ksp going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll leave a link in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the rest of this school year, so if you'd like to be notified every time I post one, subscribe to the channel, click the bell notification. So solubility and Ksp, and this is going to be the foundational lesson on what we're going to call solubility equilibria. In the last chapter, we dealt with acid-base equilibria, and we saw that for a weak acid dissociating in water, the equilibrium constant for that reaction we called Ka, and for a weak base dissociating water, we called the equilibrium constant Kb. And when water dissociated in water, i.e. the auto-ionization or auto-dissociation of water, we called it Kw. Well, now we're going to have another special equilibrium constant for another thing dissociating in water. And in this case, it's going to be any ionic solid dissociating in water. And we're going to call the equilibrium constant for that Ksp here. So and it turns out the Sp stands for solubility product, and the Ksp is sometimes called the solubility product constant. But it's just a special equilibrium constant for an ionic solid dissociating in water. And the key is you got to realize it's dissociating into its ions. So first question we're going to deal with here is what is the molar solubility of AgCl? And then the Ksp is given as 1.8 times 10 to the negative 10. And so if we're talking about AgCl, what you got to realize then, if we're talking about Ksp, then solid AgCl is your reactant. So you're always going to have a solid reactant if you're doing any kind of Ksp reaction. And in this case, it's just going to dissociate into its individual ions. And so we're going to get a single silver ion and a single chloride ion. And it's just one of each because there's only one of each in the formula. And then the equilibrium constant expression for this, that's what Ksp is. And so in this case, we're going to get the silver ion concentration times the chloride ion concentration, and then it's all over 1. So if you recall, with the equilibrium constant expression, solids do not appear. They have an activity of 1, and so that's why it's left out, and that's why they call this a solubility product. Product meaning multiplication here, because you just have the product showing up, but never the reactants in a Ksp expression, so you're never going to have a denominator in a Ksp because your reactant's always going to be a solid here. Now if we set up an ice chart here, real quick, and normally I'd just say, well, there's no point in setting this up for the solid. So, because we don't need to know anything about the amount of solid according to the Ksp expression anyways, it doesn't appear there. So there's no point in filling this in, but we're going to go back and change that for a second in just a little bit for one specific reason. So, but in this case, before AgCl dissociates, my question for you is how much Ag plus and how much Cl minus should there be in pure water before any AgCl might dissociate in that water? Well, if you live where I live, in Tempe, Arizona, there might be some. But hopefully if it's really pure water, so these are supposed to be zeros initially. And then as they dissociate, you're going to get a change of plus x and plus x. We typically write changes in these ice tables as in terms of x, and with coefficients of 1, it's just 1x and 1x. And then for at equilibrium there, 0 plus x is x, and 0 plus x is x. Now the important thing is I said I was going to fill something in back over here, and we're going to do that. And the only part I really care about filling in is the change. And based on the 1 to 1 to 1 ratio, so this is going to be a minus x. And that's important. So this x, it turns out, is the molar concentration of the solid that dissolves in water. And that gets a special name. We call that the molar solubility. So special name, and it's always going to equal x in the ice chart. And even if you don't just have one of each of the two, one of the cations, one of the anions, if it's a 2 to 1 ratio or 1 to 2 ratio or whatever ratio it is, so it's still just going to be a minus x here if you filled in the ice chart for the solid, and it always is just going to be the molar concentration of the solid that dissolved. And so x, by definition, equals this molar solubility. And so it's really quite common to be given one of two different questions, either to be given the Ksp and asked to solve for the molar solubility, which is what we're doing in this question, or to be given the molar solubility and then asked to solve for the Ksp. That's probably the two most common questions in this section on solubility equilibria. All right, so in this first one, we're asked to solve for x, the molar solubility, but we are given the value of the Ksp, and the value of the Ksp we were given is 1.8 times 10 to the negative 10, and that's going to equal x times x, or just simply x squared. And so to solve for x here, we're simply going to take the square root on both sides. Good time to pull out that calculator. In this case, the square root of 1.8 times 10 to the minus 10 turns out is 1.3 times 10 to the minus 5, has units of molarity here. And that is your molar solubility. That is the concentration of AgCl that dissolved. Now, instead of asking you just for the plain old molar solubility, we could also ask you for the concentration of either one of the product ions. But in this case, they're just equal to the exact same number, 1.3 times 10 to the minus 5 molar. So it wouldn't really be a new question. However, if we had coefficients in front of here, like we will in some of the other examples, that would change some things. These product concentrations don't have to be equal to the molar solubility itself, but might be equal to some multiple of it, as we'll see. Cool, but that's the first answer here. 1.3 times 10 to the minus 5 is the molar solubility, is X from the ice table. Second question, what is the molar solubility of Ag2S? And the Ksp is given as 6.0 times 10 to the negative 51. So super small Ksp. Notice we had one that was 10 to the minus 10 already. Now it's 10 to the negative 51, even smaller. And that's evidence that you get even less products than before. So typically the lower the Ksp, the smaller the concentration of products you're getting, and the less of dissolved solid that you're going to get as well. So larger Ksp means more soluble, smaller Ksp means less soluble. However, we've got to be careful when we're actually comparing two different ones, as we'll see at the end of this lesson. So, but for this one, we're just, again, asked the exact same question as the first one. So the Ksp is given, and we're asked to solve for the molar solubility, X, yet again. And so we'll set this up one more time. For Ksp, it's always an ionic solid dissociating into its ions. In this case, we're going to get 2 silver ions plus 1 sulfide ion. And if we set up that ice table, once again, if we cared to set it up for the solid, that's the only part that really mattered. So, but on the other side here, 0 and 0, before any of that silver sulfide dissolves, there should be no silver ions and no sulfide ions in your water. So, but instead of plus x here for the silver, it's going to be plus 2x. So, and in this case for the sulfide, just plus x. And 0 plus 2x is 2x, and 0 plus x is x. So, and the other half of the equation here is we never set up the Ksp expression. Let's do that. So it's going to be a little bit different here as well. And again, it's just products over reactants again, but the reactants of solids never going to show up. So, but here we got to remember the square, that silver ion concentration. So it's Ag plus squared times the sulfide ion concentration. And now when we go to solve for x and we substitute things in, so again, the Ksp is given as 6.0 times 10 to the negative 51. And that is equal to the silver ion concentration at equilibrium, but I have to square it as well. So notice that 2 is showing up in 2 places. It's showing up in front of the x here as 2x, but it's also showing up as the exponent because coefficients show up as exponents. So it is indeed showing up in 2 places here. And then times the sulfide ion concentration, which is just x. And so when you square 2x, most common mistake students make here is they square the x, they forget to square the 2. And so 2x quantity squared is not 2x squared, it's 4x squared. And then times another x is 4x cubed. And again, that's equal to 6.0 times 10 to the negative 51. We'll divide both sides by 4. We'll definitely use a calculator for this. So 6e to the negative 51 on my calculator divided by 4 is 1.5 times 10 to the negative 51. I guess we could have done that in our heads. And now we want to take the cube root to get there. And so how do you take a cube root in your calculator? Well, you've got a couple different ways. A lot of you guys will have a special math function for cube roots and stuff like this. So, but what you can also do is just use your caret button. And so we'll take 1.5 times 10 to the negative 51 and then caret, and then put in parentheses the 1/3 power, because the cube root is the same thing as the 1/3 power, just as a square root is the same thing as the 1/2 power. And put it all in parentheses so it makes sure that it's all the power expressed there. And so in this case, the 1.5 times 10 to the negative 51 to the 1/3 power is 1.1 times 10 to the negative 17. And again, that has units of molarity. And in this case, again, that's the answer we're looking for. That is the molar solubility X. Now again, a couple different questions I could ask you. Instead of just asking for the molar solubility, I could have asked you, what is the sulfide ion concentration in a saturated solution? We tack on that saturated solution because that means that the most that could dissolve in that solution has, and it usually doesn't take a whole lot. So, but because you could have, just a tiny bit of solid and it all dissolves and you don't actually reach the maximum concentrations possible. But if you have a saturated solution, it means bare minimum, you've added enough solid that maybe there's just a little bit left over, or you're right at the point where there would be some left over, and it's saturated and you will hit the maximum concentrations that we calculate using our ice table here. So in this case, the concentration of sulfide is simply just that same number. So the molar solubility, 1.1 times 10 to the negative 17 molar. But if I asked you, what is the silver ion concentration in a saturated solution? Well, that's not equal to X, it's equal to 2X. And so you'd have to double this to 2.2 times 10 to the negative 17 molar. In fact, if we had to carry some extra sig figs, we might actually see it probably would round up to 2.3 times 10 to the negative 17 molar. Cool, and that's a little bit tricky, and a lot of students say, wait, Chad, that's wrong, because you gotta square it. Well, again, the question is just, what's the silver ion concentration? The Ksp formula says when you have a silver ion concentration that you square it when you're plugging into the formula, but the concentration itself is just equal to 2x. 2 times this 1.1 times 10 to the negative 17 molar. So be careful with that. All right, so that's our first two. We're given Ksp and asked to solve for the molar solubility X. So in this next one here, it's going to be the exact opposite. It says the molar solubility of bismuth 3 iodide, BiI3, is 1.32 times 10 to the negative 5 molar. Calculate Ksp. So this is backwards now. Now we're going to be given X and asked to solve for Ksp. Let's get a little room here. All right, so I cleared off quite a bit of the white space here, but I kept this because I'm going to reference back to this later. And when I say later, actually not in this lesson, but at the beginning of the next lesson. All right, so in this case, again, we're given the molar solubility of bismuth iodide. We're given X, and now we're asked to solve for Ksp. And again, be very careful on your terminology here. When they give you the molar solubility, notice it has that word solubility in it. But don't forget that Ksp itself can be referred to as the solubility product constant, and that also has the word solubility in it. So know the difference. Molar solubility, that's X. Solubility product constant, that's Ksp. And they could have phrased it that way as well. But in my case, I just said, what is Ksp, or calculate Ksp. So if we take a look at bismuth iodide here, once again, it dissociates to give you Bi3 plus 3I minus. And in this case, your Ksp expression, bismuth concentration times the iodide concentration cubed. And where do we go from here? Well, if you fill out your ice table again, you can kind of probably envision this. You're going to have 0, 0, plus x plus 3x, and then x and 3x. And then we're going to substitute those back in here, and we're going to have Ksp equals x, and then plug in 3x for the iodide, and we'll go from there. Now, one thing to note, really common to express Ksp in terms of X, the molar solubility. And there's a shortcut when you're doing for this. And it works in this kind of a question where you're just dealing with solubility. In the next lesson, we're going to learn about common ion effect, though, and precipitation and things. And you'd never want to do the little trick we're about to do in one of those problems. And we'll see why when we get there. So you really got to understand the different types of calculations you might be asked and when it's appropriate to use one pathway versus another. But the shortcut I like using when I'm just relating Ksp to the molar solubility is I look at my formula here, bismuth iodide, and I say there's one bismuth, and as long as I'm just relating Ksp to X, the molar solubility, with no common ions present, which again is referencing the next lesson, so then I say there's one bismuth, and that's going to be 1x to the 1 power. There's going to be 3 iodide ions, so that's going to be 3x to the 3 power. And notice that's just what we ended up with in following kind of setting up the ice table, setting up the Ksp expression. So this is just a shortcut for quickly writing Ksp in terms of X, the molar solubility. Now in this case, again, don't forget that you've got to cube, when you cube 3x, the whole quantity, you've got to cube not just the x, but also the 3. And 3 3 cubed is 27. And so you're going to end up with 27x cubed times another x is going to be 27x to the fourth. And so in this case, we've got 27x to the fourth, and again, x is the molar solubility, and that's what was provided in this question as 1.32 times 10 to the negative 5 molar. And we're just going to substitute it in for x right there. And so you're going to get your Ksp equal to 27 times 1.32 times 10 to the negative 5 to the fourth power. And if we do some plugging and chugging here, so 27 times, and I'll use parentheses, 1.32 e to the negative 5 in my parentheses, and then to the caret fourth power. We're going to get 8.197, so 8.20 times 10 to the negative 19. Cool, so actually exactly the opposite fashion as the first two questions. Instead of being given a Ksp and asked to solve for the molar solubility x, here we're given the molar solubility x and asked to solve for Ksp, so exactly backwards. So in this last question, we are given 5 different salts here, ionic compounds, and their corresponding Ksp values. And then we are asked to find and choose whichever one has the highest solubility in water. So gonna be a little bit tricky here. So you might be tempted to just look at these and be like, well, whichever one has the highest Ksp wins. And it turns out maybe that'll work and maybe it won't. So the question wasn't which one has the highest solubility product constant, because if that was the case, well, then AgCl would win at 1.8 times 10 to the negative 10. But the question was which one has the highest solubility, which is molar solubility if you want to look at it in terms of molarity. But in this case, the highest solubility means the highest value of x. And in this case, you can't just compare apples to oranges, as we'll see. So if you look at like AgCl, AgBr, and AgI, these all dissociate into exactly 2 ions. 1 silver and 1 chloride, 1 silver, 1 bromide, 1 silver, 1 iodide. But it's exactly 2 ions. And as a result, for every single one of these 3, you'd have Ksp equal to x squared, and so x would equal the square root of the Ksp. So, and in this case, because they all have this relationship between the Ksp and their molar solubility, well then, yeah, if I want the largest value of x, well, whichever one has the largest Ksp would have the largest value of x. Okay. And so as a result then, in comparing AgCl, AgBr, and AgI, I could just compare the Ksps. So, and because AgCl's got the highest of the Ksps out of those 3, then we could get rid of these other 2 as possibilities. We'll rule them out. So, but however, with Ag2S and COOH2, these dissolve into 3 ions, 2 silvers and 1 sulfide, 1 cobalt, 2 hydroxides. And because they dissolve into 3 ions, so and recall my little trick here. So with like the silver here in this case, because there's 2 silver ions, that's going to be 2x to the 2 power for my Ksp. And with 1 sulfide, that's going to be 1x to the 1 power. Well, with cobalt, it'd be 1x to the 1 power and then 2x to the 2 power, which would be just this in reverse, but it's going to be the same thing. But the key here is then Ksp is going to equal 4x cubed, which means x is going to equal the cubed root of Ksp over 4. And so in comparing these 2, since they're both going to follow this same exact formula right here, let's get this out of the way for clarity's sake. So then, yeah, between these 2, whichever one has a higher Ksp is going to have a higher value for x, a higher molar solubility. Well, in this case, I can definitely see which one's higher. 10 to the negative 15 is definitely larger than 10 to the negative 51. And so we can get rid of these right here. And so the question then becomes, in comparing AgCl and COOH2, which one's going to have the higher x value? Well, the problem is they follow 2 different equations as they're related to Ksp, and so I can't just say whichever one has the higher Ksp wins, because they got 2 totally different formulas. So which one will have the highest value for x? Odds are, good chance you're doing a calculation here, unless you can ballpark it in your head. Because if you notice, here we're doing a square root of Ksp. Well, square root of 10 to the negative 10 is 10 to the negative 5. And so it's going to be somewhere in the neighborhood of 10 to the negative 5. Whereas here, we're taking a cube root. But it's not just the cube root of Ksp, it's the cube root of Ksp over 4. Now, if you notice, our Ksp here is 1.3 times 10 to the negative 15. Well, again, 10 to the negative 15, if you take the cube root, that would actually be 10 to the minus 5 as well, because 10 to the minus 5 times 10 to the minus 5 times 10 to the minus 5 is 10 to the negative 15. But we're not just taking the cube root of Ksp, it's the Ksp after you've divided by 4. Well, if you take 1.3 times 10 to the negative 15 and divide that by 4, you're going to have something times 10 to the negative 16, which is going to be even smaller. And maybe it's not quite as big as 10 to the negative 5, but it's still in that ballpark and probably worth doing the calculations here. So for AgCl here, we're just going to take x equaling the square root of 1.8 times 10 to the negative 10. And we already figured out that that was going to equal earlier 1.3 times 10 to the negative 5 molar. And in the case of the cobalt-2 hydroxide here, x is going to equal the cube root of 1.3 times 10 to the negative 15 over 4. Now let's see what that comes out to. All right, so 1.3 e to the negative 15 divided by 4 is 3.25 times 10 to the negative 16, and then caret to the parentheses 1/3 power, it's going to be 6.9 times 10 to the negative 6. And indeed, it wasn't quite as big as 10 to the negative 5 molar in this case, but was still in that 10 to the minus 6 molar range. And as a result, 1.3 times 10 to the minus 5 is definitely bigger than 6.9 times 10 to the negative 6. And so out of these 5 salts, AgCl is definitely the most soluble, has the highest solubility in water. And again, had you just looked at these and said, oh, whichever one has the highest Ksp wins, you would have coincidentally been correct. So, but professors are really good at choosing an example that it works out the other way. And it's not necessarily the one with the highest Ksp, but you actually have to do some work and figure out which one truly has the highest X value. But notice the strategy here is just find the salts that all dissolve into the same number of ions, and your highest Ksp has the highest solubility out of those 3, or 3 in this case, or the lowest Ksp is the lowest solubility if they're asking the question exactly backwards. And then again, these two both dissolve into 3 ions, so they're going to have similar equations, and whichever one has the larger Ksp is more soluble, whichever one has the smaller Ksp is less soluble. And then you can compare one from each group, and you might actually have to do a little math just as we've done. Now, if you found this lesson helpful, that thumbs up button is pretty much the best thing you can do to support the channel and make sure that other students get to see this lesson as well. If you are looking for practice problems or study guides or practice final exams and final exam rapid reviews, take a look at my General Chemistry Master Course. A free trial is available. I'll leave a link in the description. Happy studying.